now let's figure out how to solve a linear system in case when the matrix of the system has complex eigenvalues, right? So if the matrix is real, so the coefficients of the matrix are real, but we have a complex eigenvalue, then let's just well, the fact that it is an eigenvalue, it means that there is an eigenvector xi, right? So it also has complex entries, and then we can apply complex conjugation. So notice that since A is a real matrix, it means that A conjugated is A itself, right? So when we apply conjugation, it changes xi and changes R, but does not change xi. So what we see is that eigenvalues and eigenvectors occur in as pairs, right? So if we have an eigenvalue and an eigenvector, complex eigenvalue and complex eigenvector, then its conjugate is also a complex eigenvalue and complex eigenvector, right? So here is an example, right? So here is a very simple example of a matrix with complex eigenvalues and eigenvectors. And as you see, eigenvalues, there are two eigenvalues and they are complex conjugates of one another. So which means that the real part is the same, but the imaginary part are minus, well, the negative of each other. And then same thing with the eigenvector. So the real part is the same, and the complex part, the imaginary part is one is the negative of the other one, right? So now we can proceed, and well, we can figure out what the complex valued solutions are, right, of the corresponding system of differential equations. And let's just explore the first of them. All right, so let's look at the first complex valued solution. So here is the first one, and of course, since it is a complex valued solution, it means that it has a real part and the complex part, right? So this is the real part, and the imaginary part, and this is the imaginary part of the complex valued solution. So now let's just do a naive thing. Let's see if whether this real part and the imaginary part are going to work separately, right? So we are going to substitute the real part. So in other words, we're going to take this and substitute as x1 and x2 into the system of differential equations and see if it gives us the correct equality. And yeah, it does. And you can do the same thing with this. You will see that it also works. That's the imaginary part. Well, and of course they are really solutions, because, well, imagine that if our x is really something like x1 plus I x2, where this is the real part and this is the imaginary part. But then, since when you differentiate dx dt, what you really have, you have to differentiate them separately, right? So you're going to have dx1 dt plus I dx2 dt, and then when you multiply with a real valued matrix, you kind of multiply them separately. So which is why it works. So now let us compute the wronskian. Okay, so let's compute the wronskian of these two solutions. So the wronskian of these two solutions is going to be what? Know that the wronskian of vector valued solutions of systems of differential equations is actually a simpler concept than the wronskian of well, solutions of higher order differential equations, because you don't need to differentiate anything. So to compute the wronskian, what you do is you just of these two, what you do is you just form a matrix out of them. So you just write them together. So in other words, what you do, let me just do it like this. So the wronskian of the system is nothing else but the determinant of this matrix. And this is minus is here, of course. Now let me take out e to the t. So e to the t from here and another copy from here. So this is e to the 2t. So the rest is minus sine squared t if I multiply like this, and minus cosine squared t if I multiply like this, cosine squared t. And this is minus e to the 2t, which is non-zero. Since it is non-zero, it is strictly negative in this case. It means that the real and the imaginary part of the complex valued solutions are linearly independent as real solutions. So therefore they form a basis of the solution space. Okay, now let me give you a theorem. All right, so suppose that A is an, well, in general case, an n by n matrix with real entries, right? And then suppose that we have a complex eigenvalue and a complex eigenvector. So then the real part and the imaginary part of this complex valued solution are linearly independent solutions over the reals of the of the corresponding system of ordinary differential equations. Now to prove it, we're going to do something, well, a little trick, right? So the little trick is that we can express this real part and the imaginary part of the complex valued solution as linear combinations of the two complex valued solutions, right? So this is the real part, and the imaginary part can be done in a similar way. So it is homework for you to figure out how to do the imaginary part. Okay. Well, but then the next thing is to prove that they are actually linearly independent, and it is going to be on homework, so you don't have to worry about it now. So which means that the general theorem that we have proved is that if A is a diagonalizable n by n matrix with real entries, right? So then if we have eigenvalues and eigenvectors, then it means that we have n linearly independent eigenvectors. That's important, right? So to say that the matrix is diagonalizable is the same as to say that we have n linearly independent eigenvectors. Alright, so then it produces n linearly independent solutions of the system of differential equations.